Hello! Today is December 11th and we're doing the challenge for day 10, so we are still one day behind and we are catching up, and yeah, that's why we're doing this. So we're solving the Advent of Code challenge while we are learning the programming language NIM. So super interesting. Today we're building a CPU that takes in some instructions. So let's go to the drawing board. So I think this example actually was really good, so I've tried to visualize it here, and let's go through it very carefully. So we get this type, we get an instruction, and there are two types of instructions in this instruction list. There is the NOOP instruction, and then there is ADX instruction. And if you've ever programmed in assembly, this is the mnemonic, and this is the operand, for example. You could think of it in that way if you're programming in assembly. All right, so what happens? The ADX instruction takes 2 cycles to complete. After 2 cycles, the X register of the CPU is increased to the value whatever is in the operand of the ADX mnemonic. And the NOOP takes 1 cycle to complete, and it has no side effect whatsoever. We initialize the CPU with a cycle count, which starts at 0, and the register X starts at value 1. So this is visualized here. So we have the initial state of the CPU, cycle 0, register 1. And then we need to keep track on something which is called the signal strength, which is the cycles times the whatever is in the register over there. Okay, so let's go through. We start here in the initial state. Cycles, 0, register, 1. We encounter a NOOP, so hard not to say noob, instruction. And so we are at the first cycle, so cycles is now 1. The NOOP instruction begins. During the first cycle, X is 1, so the register. After the first cycle, the NOOP instruction finishes and does nothing. Okay. Now we come to the second cycle. We encounter an ADX 3 instruction. So the instruction begins execution. During the second cycle, X is still 1. So we're here. Cycles 2, X is still 1. And then where are we now? Now we're at the third cycle. So X is still 1, but after the third cycle is finished, we set the register to 4. So there, it increments it. So yeah, so remember that we have X amount of instructions, but we have a Y amount of cycles actually, and these are not, so it's not 1 cycle per 1 instruction. I think that will be like a common pitfall in this, that you think like 1 instruction takes 1 cycle, but no, this is not the case. And so what we want to do is we have this long list of like NOOPs and ADXs, and then at the end we just take the signal strength at the 20th, 60th, and these cycles. So we check what is the signal strength during those, and we take the sum of those, and that will be the answer to our challenge. So yeah, if this is confusing, no worries. I think this will get more clear as we program this out. So we have to like explicitly express everything when we program. Yeah, that's gonna be really nice. Let's code. Like that. Do you know, sort of like when children learn a new word, then they sort of like put that word everywhere. I feel like this is kind of similar, that when you learn how to do something in a new programming language, or you learn like, okay, so this is like how you do that data type, then you do everything in that. I don't know if this is kind of like unnecessary for this task to make it like this. I mean, we could just have like simple if-else statements, and we're gonna have for sure, but I don't know, it's just fun. So now we have the two cases here. So now we're iterating over the instructions, and now for each instruction we have the case, what are we gonna do when we have a NOOP. So if you remember, we're just gonna increment c.cycles, and then if we have an ADX, we're actually gonna do it for I in 0 to 1. So we're gonna increment c.cycles, and if because it takes 2 cycles, so if I equals 1. Then we're also going to set the C dot register, and that should be plus equals the instruction dot operand. I think that's correct. So let's do some echo C, and actually, yeah, we need to implement a way of. Let's quickly do that actually. Okay, so let's see. So I have here in the test, I have just the 3 instructions as we have here in the example, and it seems to be going correctly. So at cycle 1, it's that, and cycle 3, it's that. And now as you see, so now we're printing these, we're echoing these per instruction and not per cycle. And this is going to be if you see now if we would implement the logic that every 20th or was like every 40th cycle we would want to do something, we are like in the wrong place of the loop, because we wouldn't be able to access each and every cycle that we have. So yeah, that's all we have to actually do the logic here within each cycle. So because the question is here, let me pull it up. So what is happening during the 20th cycle? And that's what we need to get in there. I think this is going to be like a common pitfall. So let's change places. We have a list of the interesting cycle counts, and now we are in the actual cycles. And if see that cycles is in interesting, then we echo it. So this should be exactly what they're after here. So we have cycles 20, then register is equal to 21, and then the signal is 21 times 20, which is 420, and so on for all of these interesting ones. And I think I'm now at like the correct. So now this is like in between. So especially if you look at this, let's actually do this as an example. So if we do this after here, which I first initially like thought that should be like the correct place. So then we can see all the other ones are correct except the last one, where the register is now 19, because we're echoing this stuff at the end of the cycle when the operand or the register has already been changed. But we don't want to do that. We actually want to echo these like in the middle, like during the instruction. And as it just like happens, it doesn't change anything on any of the other ones, just because like it happens that the one like before or after is the same, or the register doesn't change. But for the last one, it does. So yeah, that was like yeah, pretty yeah. You should be wary about that potential mistake. Is it like, does this make any sense? Does this make any sense? Well, maybe it does, maybe it doesn't. Let's see. And it did make sense. Yes, 1 gold star to part B. I've been looking at the part B for quite a while, and it actually took me a long time to even understand what's going on. It's like just wrapping your head around to understand the assignment is like one hell of a task. But I think now that I have sort of like understood it, I don't think it's super hard to implement, but I think this is like a challenging one to wrap your head around it. So I will try to explain this to you. I won't even try like drawing it. It's gonna be, yeah, that's just gonna confuse you more. So yeah, let's give it a try. So we have 2 new things here. We have a sprite and we have a CRT. So the CRT is basically, you can think of it like as a small screen. That's yeah, basically this, and each hashtag is a pixel. And what we are doing here, so for each cycle of the CPU, we are determining whether that pixel should be on or off. and it's on if there's a hashtag, and it's off if there's like a dot. You can see here like the final version, it becomes something like this if you when you run the example instructions. And so how now comes the tricky part, like how do we determine whether the pixel should be on or off? Well, for that we have the lovely concept of a sprite, and the sprite works followingly. So during the CPU cycle, we look at the register. So in the beginning, the register is 1, and then we sort of like in the sprite. So this would be the sprite in the beginning. So at index position 1, and then we also have like we have +1 and -1. So like 1 on both sides of the actual index position. We have in those places the sprite is activated basically. And then we just simply ask, like, is the current cycle, is that within the sprite? So yeah, that probably didn't sound like let's try again. So we are currently on cycle 1, which means that we are determining whether pixel 1 should be on or off. And then how to determine that is that we're saying that, okay, pixel number 1 is 1 within the range from 0 to 0, 1, 2. Well, yes, it is. Therefore, we light the pixel. Okay, let's do one more. So now we are on cycle 2. So we're determining whether the pixel 2 should be on or off. And in this case, yeah, exactly. In this case, we haven't, like, the register hasn't changed yet at all. So now, yeah, the register is still in position in 1, and 2 is within this range. So that's why that is on. But now comes a different case. So now we are finishing executing the addx15. So now the sprite is in this position. And now we ask, we're on the third cycle. So now we ask, is 3 within 14 to 16? And no, it's not. So therefore, the pixel is not on. That's something to wrap your head around. Yeah. Let's start coding that stuff, right? CRT is a ref object, and it's just gonna have a data field, which is an array from, yeah, basically like 40 times 6, because that is the sort of like range we are moving in, or like that's this. I'm gonna do it in the same way as I did the, what's it called, the matrix. And I want to be able to visualize it beautifully. And then let's not have that. We can do system.quit. So we're not even executing that, and we can do that. And that's not how we want it. So now we have the basic CRT setup working. So now for the tricky part. So now implementing the logic, whether the pixel should be on or off. And now, like, hold tight. This is gonna be heavy. So we need to look if the CDOT cycle is within a range of the CDOT register, and that particular range is like ±1. Another way we can like check that is if we take the absolute value of the difference and ask if that is like smaller or equal to 1. Okay. And so we can say if this is true, then we want to say like a CRT dot data at c.cycles should be changed to the hashtag. And yeah, I was expecting something like this, so that the first row would be stuff like this, and obviously it wasn't that, because I wasn't reading in the test, I was reading in the input. So yeah. So now, okay. Now you see. Okay, but now, as you can see, we have a problem. So after we go, uh, after the first, what's it called? Row. After the first row, we are not doing this stuff anymore. Uh, what happens? We have a problem. And the problem is here. So remember our sprite, it's only from 0 to 40, but our CRT is from 0 to from 0 to 240, or from 1 to 240. And the problem is that when we're doing this check and we go below, not below, when we go like past the first line, then these sort of like aren't indexed correctly. But I think I have just a trick. So if we do modulo 40, which is the, what's it called, like the, you know, the width of the whole CRT, then this should work, because now we're checking like we're taking into account like at what row we are. We are, so to speak, we are dividing by like the amount of rows, so that like so let's say for example if we are here, so which is 201, so then it gets translated so that we can compare it to the sprite position, which is always between 1 and 40. 0 and 40, I think. So now let's move on. Let's keep the animation rolling. Okay, it does not really work. The problem was that we had, because this is of course done first, and then like this is done. So you first do the modulo and then the minus. And I previously had cycles and registers here. So I was checking the modulo on the register, not on the cycle. But I want to do it on the cycle because the cycle is the one that goes above 40. So now when I do this, as you can see, it works. And if we like scroll, go on here. And now you can see that this is actually valid to what we have here. So now let's clean this up. The question is, what 8 capital letters appear in your CRT? So let's see. Okay, so what is this? Oh my god, this is difficult to read. So is that E? E, R? Is this supposed to be readable? Yes! Nice. Nice. That was good. Okay, so part B. Yeah, very difficult to understand, but once we nailed this thing correctly, this was actually quite sort of like, it wasn't a lot of code changes, but it was like a lot to wrap your head around. And I can imagine, like, if you didn't get this right, like debugging this, like, damn, that would have been and in fact, I did some debugging on this, or actually quite a lot. But yeah, this probably a place where a lot of people stuck in. I can definitely imagine that. Otherwise, I think we somewhat over-engineered a lot of stuff with like making our own custom types for every opportunity we get. But at least I didn't make a custom object for the stripe. That's I left just like to be like that, which was a lot cleaner, I think. So yeah, and I still have one left, so that I'm caught up in the progress. So now let's put this away, and now I should move on to actually today's assignment. So see you soon.